Okay, we're looking at Chapter 9 today, which deals with all things about gases. Alright, first thing to keep in mind, a gas is the simplest one to look at. It's the one around us all the time. So it's our atmosphere. Now, what they're showing here is just the actual pressure you're experiencing at sea level at any given moment. Technically, there's about 14.7 pounds of pressure pressing on you at any given time, which is why the picture shows the nice little, looks like a bowling ball. That is what they're, what you would compare it to. A little 14.7 pound bowling ball sitting on your thumb is about what you're experiencing at this present moment. Don't notice it because it's always been there. But if we were to remove it, you would definitely notice it. So if you went too high up, you would definitely notice that lack of pressure. Okay, now that pressure can be measured, and one of the earliest ways to measure it is a barometer. Now the barometer, or the earliest idea of a barometer, ended up having mercury in there, which is what they're showing here. Now the reason that was is if we actually filled a vacuum tube up with, vacuum tube and then put it down in water, the atmosphere would push down on the water enough that it forced water up in that tube about 10 meters. So if we wanted to make a barometer out of water, it'd have to be like huge. But mercury being a tremendously heavier, more dense metal, it only goes up about 7/10 of a meter, or 760 meters at standard atmospheric pressure. Now that 760 that I just said being standard pressure, that's what we find is the average pressure at sea level on Earth. And on this next page we have that same pressure in multiple different units. So there's that 760. So a standard pressure in millimeters of mercury was 760 millimeters of mercury. So I can, if this thing likes me well enough, I'll put 760 here for those. Now, the other ones listed on this are just other ways that we see pressure measured in even the science world. We have multiple units. So Pascal and kilopascal are your SI base units, and atmospheres is the one we're going to mostly use here. So back when chemistry was first starting to study pressures, they needed a basic idea of what was a standard atmosphere, and they just decided one. Now the others are used a little bit less common in our class. PSI, about the only time we'll hear about that talked about, that's that third one on the list, is talking about pressure in your car tires. And of course inches of mercury would be equivalent to millimeters of mercury, but we're not using that. They still see it pop up in some weather reports and some in the aviation. Same as bars and millibars. They're both mainly in the weather reports. Although nowadays, if you watch the weather, they typically talk about high pressure or low pressure, but they don't really talk about a numerical value anymore. So the arrows are the ones that we're going to need, and anytime you need that conversion, the conversions are typically provided on the periodic table. Alright, a manometer is how we study that pressure in a closed laboratory setting. So it is using mercury, but the benefit of using mercury is that air can't really penetrate it. No gases really can. It almost behaves like a metal, even though it's a liquid, and they just don't penetrate that liquid too often, or at least not that we have to worry about it. And then the neat thing about using mercury, if you just measure the difference on heights between the two columns, you have a pressure in terms of mercury. So even though it's a distance, millimeters of mercury is a pressure unit. So what they're showing here on this first one, this first picture over here, this far left, what we have is we have a sealed container and a sealed vacuum tube. That height is the absolute pressure of that actual gas. So if this was just like 10 millimeters, that's saying there's 10 millimeters of pressure inside that container. Now the next two, the next two have the end opened up to the air, So if we were dealing with atmospheric pressure of 760 millimeters of mercury, or standard atmospheric pressure, with this height being lower, it's telling us the outside pressure is more. So we would just take that 760, subtract whatever this difference is, and this new lower pressure is that pressure inside the container. And this is higher pressure because if you notice the open air is higher up, so this is a value larger than the atmospheric pressure. But that is more beneficial when we have more pressures closer to atmospheric pressure, and this first one is closer to a small value. Would be a fun thing to play around with in a chemistry lab setting, but mercury is kind of dangerous, so we don't do this too often. Alright, on to some of our properties of standard gases and how pressure, volume, and the amount and the temperature all relate to one another. Now, to a degree, these are common ones that you might know. I mean, we could bring up YouTube right now and look at a video of throwing an aerosol can into a fire pit. Makes for interesting videos. Not very fun thing to do yourself, but if you're interested, there are some pretty interesting experimental chemists. I would recommend watching the video, not doing it yourself. Alright, first one we're looking at is one of the earliest laws that was studied very, very well. It actually gets credited to two different people. And basically all we noticed here is if you have a nice sealed container and you heat it up, the pressure inside that container goes up. Now, there was a Catholic priest who studied it a little bit more detailed and got some actual numbers. And he found that it's a nice little, very predictable relationship in the sense that as the pressure goes up, the temperature goes up, and it's a nice linear relationship. And he actually came up with this nice little equation. So if you had a relationship between the pressures and the temperatures, it was consistent as a ratio all the way along. It didn't matter what the other things were going on. If you actually studied the pressure and temperature in two different cases, you'd find the same ratio at any given moment. Now, this did need to be something special. He needed what we call an absolute temperature scale, so a temperature scale that doesn't go below 0. Because if you think about it, if you were to do this at 10 degrees Celsius and this one at negative 10 degrees Celsius, the only way to take care of that negative with this over here would be to make one of the pressures negative. So you need a scale where the temperature goes down to 0 only, which is why this is shown up with a Kelvin scale. Now the next little relationship we're looking at, this is the guy who actually first predicted what absolute 0 was. He did it in terms of volume. He found a similar relationship to the one we just had. Turns out if the volume and the temperature studied, you see that they're in the exact same ratio. Volume approaches 0 as the temperature approaches 0. And way back in the 1800s, this guy Charles predicted that absolute 0 was right around 273 degrees below 0 on the Celsius scale. And he did that without even getting anywhere close to it, because if you think about it being a nice straight line, which is what it's showing here, even if we knew this up here, higher temperatures, you should be able to extrapolate down and how far it goes down, as long as it's a nice straight line. And Charles was able to show that. Alright, the next little relationship we studied was this guy named Boyle, and he found that pressure and volume are related. So this is like, think of a bicycle pump even. As you decrease the volume of a bicycle pump, it shoots the pressure up. That's the whole point of using a bicycle pump. So that's why this has a different curve to it. What it's saying is, as we go down on the volume, pressure goes up exponentially. It actually goes towards infinity, which is why it gets harder and harder to push down on a bicycle pump the smaller it gets. Boyle was able to find that we do get a straight line, but we have to take the inverse of the pressure. Right, but that actually means we have a different type of relationship here. Turns out the pressure and volume multiplied to each other is always constant. Alright, got one more little interesting feedback that we found. Turns out you double the amount of stuff in a balloon, like we're showing here, it would double its size. So what I mean by that, if we knew the volume, and we knew the amount in there, maybe in terms of grams or moles, if we were to double that amount, we should double the volume. That makes sense, right? You double the amount, you double the volume. Well, when the early scientists were first studying this, they found out something interesting. The volume of a balloon with an air in it had to do with the moles of the gas that was in it, not the mass of it. So if you look down here, all these masses are different. Well, if we look at the periodic table, we find out that that's 1 mole of helium, and this is 1 mole of ammonia, and this is 1 mole of oxygen. So every single one of those is 1 mole, and when they studied this even more, they found out something even more neat. Each one of these volumes is exactly the same, and they are all right at 22.4 liters. Matter of fact, at standard temperature and pressure, standard temperature is 0 degrees Celsius, standard pressure is 1 atmosphere or 760 millimeters of mercury. That's your standard temperature and pressure. When you're at standard temperature and pressure, we know that 1 mole of any gas is equal to 22.4 liters, almost always. Now that does vary when we actually go, that ratio varies as we go higher and higher in the amount. Like especially if we start messing around with the temperature and the pressure, so we get away from STP. And if we go out 1 more digit, there's some variation. But for the most part, that's set in stone, that 22.4. But it does make for some pretty neat effects. Mainly, we know a helium balloon floats. Biggest reason it floats, it weighs less than the air that it displaces. Because the air that it displaces is closer to this oxygen balloon. This physically weighs less. So the helium's floating in the air because it weighs less. It's going to go high enough to, it's going to keep on going higher until it gets to the point where it weighs the same amount as the air it displaces, or the balloon pops. Alright, the guy who studied that was the same guy that we introduced way back in chapter 1 of our textbook, or 2 or 3, depending which textbook you're dealing with, John Dalton, who came up with the postulates of what an atom actually is. Well, he also studied gases, and he found out something neat. He found that the gases actually kind of ignore each other when there's mixtures. So what we're showing here is we have 3 different gases, and we have the pressures in each one of these little containers. 300 kilopascals, 600, and 450. And if we were to combine them all in the exact same type of container, turns out the total pressure is just going to be those 3 added together. That actually works always like that. The pressures just add right up. It's a nice little feature. They're not going to really interact. Now that's not always the case. Sometimes there are chemical reactions that occur, but if there's outside of that, as long as the gases are just mixing, like the oxygen and the nitrogen in the air around us right now, they are behaving as if they're individuals. Alright, once we see all that, rather than actually try to memorize all those little individual equations we wrote down previously, we're going to combine them all into one nice little rule. Alright, turns out we can actually combine them so it looks something like this. Excuse me. So, if you needed to find any one of these, excuse me, that's the nice little ratio that will always work. Now, if we actually were to study that STP set of conditions, we get something kind of neat. So, standard temperature pressure was 1 atmosphere. And remember I said that 22.4 liters? And we'll just say 1 mole of a gas. And standard temperature was 273 Kelvin, or 0 degrees Celsius. If I throw this into my calculator, and I have it right here, one times 22.4 divided by 1 and 273, we get this weird number. And if you remember in introductory chemistry, or any chemistry you might have seen before, you might have seen this number, 0.08206, with the units of liters and atmospheres, moles and Kelvin. And we actually call that R. R for the gas constant. Well, that is actually the case. In most cases, when you're near standard temperature pressure, these four terms multiply always together to give you this 0.08206, which is where we actually get this nice little equation. Alright, so we have two different equations we end up using most of the time. One's when there's two different sets of conditions, so either two pressures or two volumes or two temperatures, and one when there's just you're giving three of the four things and you need to figure it out for a single set of conditions. And we're going to practice some of those now. So I'm going to go back over to here because I can write better on this little screen. And bring up the calculator. Alright, so we have this nice little question. When filled with air, a typical scuba tank with a volume of 13.2 liters has a pressure of 153 atmosphere. If the water temperature is 27 degrees Celsius, how many liters of air will such a tank provide to a diver's lungs at a depth of approximately 70 feet in the water where the pressure is 3.13 atmospheres? Alright, little strategy. If you notice here, we have two different pressures. So just noticing those two different pressures, I know I'm going to be doing that where I combine these. Where I compare. So that first set of conditions I gave you. Alright, but there's some of these things that aren't really changing. While I do give you a temperature of 27 degrees Celsius, we don't talk about the different temperature difference. So we are assuming it's 27, so the temperature must be consistent in both. And also the air. Now obviously if you're really diving, you're going to use some air going down, so that volume would drop. But you want to know roughly how much there is altogether anyway, and so we're talking about when it's filled with air, so the moles don't really change either. So the only two things that we're really looking at changing is the pressure. And that's true, because if we look at this, I gave you 13.2 liters, and we want to know how many liters are at the lower depth, and I gave you the two pressures. So we have a nice little mathematical thing that looks like this: 153 atmospheres and 13.2 liters equals pressure. Second case is 3.13 atmospheres, and we are going to solve for this new volume. Only thing you have to watch out for, we want to make sure the units are the same. The only unit we will have to change always is the temperature. Always needs to be Kelvin, and technically the N needs to be moles. But this could have been, the atmospheres could be in pascals. We just wanted to be the same units on both sides. And same with the volume. We need to be having the same units on both sides. Alright, but to do this math, we're going to do 153 times 13.2, and then we're going to divide that by 3.13 and get a volume of 645 liters. And if I was a diver, I might have an idea of how much you can breathe with that, but I have no idea how many liters of air you take in a moment. Oh, alright, next problem. Another one of these. Alright, cyclopropane, a gas once used with oxygen as general anesthesia. It's composed of 85.7% carbon, 14.3% hydrogen by mass. Find the empirical formula if 1.56 grams of cyclopropane occupies a volume of 1 liter at 0.984 atmospheres and 50 degrees Celsius. And we want to get the molecular formula. Alright, so the empirical formula we're going to get from just these two numbers. We're going to do this very much like we did several chapters ago. So I'm going to turn these into masses by assuming we have 100 grams of that particular sample, and then do our grams to mole conversion for each one of these. Because if you remember back when we introduced empirical formulas, we can't actually get that value or that ratio from just their masses. But if I know how many moles of each of those have, there are whole mole fractions. Alright, so that is 7.14. And G, 14.3 divided by 1. And you think in your, think, back up here. What we're going to do is divide both these by the smallest. I get roughly 2. So that tells me that the empiric formula of this cyclopropane is just CH2. Alright, now if we think back to when we first introduced the concept of empirical formula and molecular formula, to turn an empirical formula into a molecular formula, we needed the molecular weight, or the grams per mole of a particular substance. Now we can figure out the empirical formula's mass. That's 12 for each carbon, 1 for each hydrogen. It's approximately 14 grams per mole. But I need to know the molecular weight of the entire molecule to know what that is. Well, I technically gave you enough because I did give you this mass. I'm going to be able to use these other 3 to get the moles because I know something kind of neat. PV equals nRT. If I have 3 of the 4 things, and I do, I have the atmosphere, and I have the volumes, P and V, and I have the temperature. I can solve for N, the moles. So that's what I'm going to do here. So I got that pressure of 984 atmospheres. I have a volume of 1 liter. I'm going to solve for that N. The R was that 0.08206. I'm just going to write R here. And I need to convert this to Kelvin. So 273 plus that 50. I get that that is 323 Kelvin. Alright, let's see if we can solve for that N. So 0.984 times 1 divided by the 323 and then also divided by 0.08206, the R. And I get that this moles is at 0.0371. Alright, well that's moles. I want grams per moles, so what I'm going to do is take this 1.56 and then divide by that value. That'll give me grams per moles. So I get that this molecular weight is 42.0. Now we just take that, figure out how many times 14 goes into it. Should be a nice whole number. In this case it's 3, almost on the nose. So we know that the molecular formula of cyclopropane is C3H6, which it is. Turns out cyclopropane only has 3 carbons. It's a nice little triangle shape. Lot of bond strain. Alright, another one of these. Alright, we have a gas mixture used for anesthesia. It contains 2.83 moles of oxygen, 8.41 moles of nitrous oxide. And we want to know that, and we're giving you the total pressure. We want to know first the mole fractions, and then the partial pressures. Alright, well, the mole fractions are kind of easy. All we have to do to get the mole fraction, now, it's got a weird little Greek letter here that we use. If I want to get the mole fraction of oxygen in this, I'm going to take the moles of oxygen, and I'm going to divide it by the moles of everything. That's all there is to a mole fraction. Moles of what you're looking for compared to the moles of everything in solution. In this case, I get 0.252. And it has no units. Now if I want to get the mole fraction of N2O, put 8.41 on top, and same 2 guys on the bottom, 2.8 and 8.41. And neat little thing we can do to check. Oh, I don't know why I put that decimal there. Because I wanted to is probably why. Alright, turns out these two should add together to give you 1, and they would. Alright, now, something that Dalton showed us. The pressures actually added up to give us a whole number. So, pressure of O2 plus the pressure into O does just equal 192 kilopascals. Alright, and they're not going to affect each other. So whatever the individual pressures are is actually going to be what we find them to be. Well, the neat thing we can do, we can use these mole fractions, because the fraction of the total, that is the O2, is what's going to give us the pressure of the O2. Or another way of saying it, the pressure of O2 equals the mole fraction of the O2 times the total pressure. So if I want to get the partial pressure of the O2, I just take the mole fraction at 0.252 and multiply it by that total pressure of 192. And we get something like that. Partial pressure of the O2 is 48.384. And to get the NO2, I'm going to take that 0.748 and multiply it by 192. And its partial pressure is, I'll do it like this, 143.6. And I guess technically both these only have 3 significant figures, so maybe I should say this was 144 and this one is 48.4. That would have been more accurate. And then units are the same pressure units. Alright. That's not coming, that's coming up. Alright, that's our 3 practice problems I'm doing here. Oop. Now we're going to introduce another concept. Alright, when we do this in a chemistry lab, an easy way to do it is this pneumatic trough idea. So on the left there, I have a little Erlenmeyer flask, and if you notice in that picture, it looks like it's bubbling. This could be ooh, I bumped my key. This could be a simple reaction, maybe just the decomposition of hydrogen peroxide. I'm going to do one that we have seen. A little bit of HCl, a piece of zinc solid. It's a single replacement reaction, makes hydrogen gas, and then some zinc chloride. I need to be 2 over there. Alright, now, the reason I chose that one is because it would be kind of fun to collect some hydrogen gas, because hydrogen gas, you take a match into it, it kind of pops on you. Would be kind of fun to do it. We're not really going to do it. We'll just talk about how we do this. Alright, so we got this little chemical reaction going on. If we were to want to do this for an actual lab, we'd want to actually get that reaction going and let this bubble out by itself outside of our collecting gas for a while, because if you think about it, when the reaction first starts, the container is going to have air in there, and we want to get that air out of there. We want to collect nothing but pure hydrogen. We have to let it react some time and force all the extra air out. Alright, then when it comes over here, what we're going to do to capture our now pure hydrogen, or what we hope is pure, is we are going to fill an Erlenmeyer flask up totally with water and invert it inside there, so no air whatsoever. And then we'll run a hose up underneath there and let the pockets of gas build up in here. So when we're all done, this should be absolutely pure H2 gas. Alright, that's the concept. It's got a problem though. Because the bubbles are going through water, we're going to saturate this air with water vapor. Alright, that's okay though, because water is very well understood, and we know exactly what that pressure will be for water at a given temperature. It actually behaves nice little curves like this. So down here, when we're closer to room temperature, it's very low pressure. Now it does vary, goes up a little bit, but we are talking very, very low. And another neat little feature that this little curve shows, it does technically end right about here. So right about 100 degrees Celsius, if you notice, this is right at 760 millimeters of mercury. The reason that's happening, what that's actually saying is The reason boiling looks like it's boiling is because we've got the liquid so hot, its vapor pressure equals that of the atmosphere, so it is very rapidly evaporating. Now, the neat thing is, and I get into a chemistry lab, we can drop that pressure down, and even in our lab, we can drop it down way down here, so even here at room temperature, we can put that into that curve right there. We can make water that's at room temperature appear to be boiling. It's fun to do it in the lab because everybody's reluctant to grab that glass because they're expecting to be super hot because it looks like boiling water. But it will be cool. It'll be room temperature. Just neat that we can get the pressure that low. Alright, when we go to apply that, we have this nice little dilemma. Now, what we got going on here is I have just 0.2 liters of argon. It's being collected over water at 26 degrees Celsius and has a pressure of 750. We want to know what's partial pressure of the argon. Alright, now we kind of can figure that out because we gave you the total pressure. So total pressure is that 750. Now it doesn't say a unit here. I don't know why it doesn't. Got the torr down here, so I'm assuming that is torrs. Typo on my part. Alright, but that's the total pressure. That is, in this case, going to be the pressure of argon. Ooh, that should be an equals. I can just change it real quick. There, now it's an equals. And the pressure of water. Well, the nice thing is, when we're right at 26 degrees Celsius, we could use a graph like this, or there's nice little tables to look up the values, and that's what I did. I found a table in the back of your book, and at 26 degrees Celsius, the partial pressure of water is 25.2 torrs. So to get that pressure of argon, we are just doing a nice little subtraction. We're going to do at 750, the total pressure, and we will just subtract the 25.2, and we get this 725. That's all there is to that. You actually can get it just by subtracting it because the gases do add together. They don't actually do any weird math. They just flat out add together. Alright, because they add together, and because they are nice little relationships, that 22.4, we can actually do chemical reactions and study the volume of gas being produced, or the pressure. And it makes for some neat little concepts too. Like, you know how we said the gases would actually add together? If I were to take a set of gases that had nitrogen and hydrogen mixed together, and even mix all four of these balloons together, it would occupy 4 times that space, right? One balloon times 4. Alright, but if they chemically react, the nitrogens rip apart and make NH3s. Well, each one of these 4 molecules only end up giving us these 2 here. Our actual number of balloons would decrease if they chemically react. If they do add together, they wouldn't necessarily chemically react. Alright, we're going to apply that in something like this. So we have, and let me go back here to this, because we're going to do some math on this too. Alright, so we have propane. Not the cyclopropane we had before. This is more like from your gas grill. We're going to calculate how much oxygen is being used to react with 27 or 2.7 liters of propane. Alright, so we have this nice little relationship going on. We have some C3H8 gas and some oxygen gas going through combustion to make CO2 and water vapor. And we need to balance this because we need to know that relationship between these two. So I'm going to put that there's 3 of these, 3 carbons, and there's 8 hydrogens, so there's need to be 4 of these. That created 6 oxygens plus another 4, so I need 5 waters. So we see for every 3 carbons, or for every 1 propane, there would be 5 oxygens. Alright, I gave you a lot of information here. Turns out this math is kind of easy if we notice something about gases, but we're going to solve it the long way first. So what I mean by the long way, we know that you have 2.7 liters of propane, we know the 25 degrees Celsius, and we know the 760. let's figure out how many moles of propane they are using the PV equals nRT. So we have a pressure of 760 torrs, but in the ideal gas law, I need that in atmosphere. So I need to take that 760 torrs and convert it to atmospheres. Alright, turns out one's pretty simple, because 760 torrs is the same as 1 atmosphere. Alright, I do want the pressure in liters, so the 2.7 is fine. We're going to solve for N. The R is 0.08206, and then the temperature is 298. I get that from 25 plus 273. Now if I did this and solve for N, I get very small value of 0.11. Alright, now I'm not going to clear that calculator because I want to actually now know how many moles of oxygen there are. Well, we know from previous things, if I had this, something like this, if this is my moles of oxygen, well, it's not oxygen, is it? That's my moles of propane. I can use that stoichiometric ratio of 1 C3H8 to 5 oxygens to get my moles of oxygen. So I'm just going to come over here and multiply this number by 5. And that's my moles of oxygen. But it doesn't want to know the moles of oxygen, it wants to know the volume. So, once I have my moles of oxygen, 760 torrs, and 1 atmosphere is 760 torrs. And we're going to solve for this volume. We're going to use this N I got, so that 0.552. Same R and the same temperature. So we are now solving for that volume. So I'm going to take this moles I just got, multiply it by R, 0.08206, and the temperature. And then technically I'm dividing it by 1, so I get a new volume, and I'm going to put it up here, of 13.5 liters. Alright, now, while that works, and that is going to work all the time, something interesting goes on with gases. Alright, the temperature and the pressure didn't really change between these two. So, because of that, we have this cool little relationship that's kind of true. That 2.7 liters, well, remember that slide a couple things, I showed these with balloons. That 2.7 liters is propane, and there is 1 C3H8 balloon for every 5 O2 balloons. So I really could have done as simple as this, 2.7 times 5. Got the same value. And that's really because the 760 and the 298 don't change. So the size of the balloons would be consistent even though they have different gases in there. It is as simple as saying what this picture was showing us. There were gas balloons. If they're under the same condition, a mole's worth of a particular gas occupies the exact same space regardless of what gas is in them. And we didn't change the conditions here, so we would expect that. Alright, now, a way that we're going to have to do some math. You notice on this problem, I give you a mass of gallium, and then I want you to calculate the volume of something else. Alright, this is going to take that ideal gas law. Alright, so here we go. Alright, so what volume of hydrogen at 27 degrees Celsius and 733 torrs may be prepared by the reaction of 8.88 grams of gallium with an excess of hydrochloric acid? Alright, what we're going to need to do is figure out how many moles of hydrogen gas we produced from this 8.8. And we're going to get that from our periodic table. Alright, so 1 mole of gallium is 69.72 grams. And from our Waals reaction, we see that there's 2 galliums for every 3 hydrogens. Alright, going to do that in my calculator real quick. 8.88 divided by 69.72 times 3 divided by 2. This is the moles of hydrogen being produced. Alright, not going to do anything with that. I'm going to leave it in my calculator, because I know the pressure torrs. I'm going to convert that into atmospheres. Take the pressure, multiply it by the volume, which I'm going to solve for. It's going to be equal to N, the moles we just think, times our R, times our temperature. That adds up to a nice number. We're going to solve for that volume. Alright, so what I mean by that, we're going to take this N, multiply it by R, and multiply it by the temperature. And then we need to divide by this thing. So divide by 723 and divide by a divide times 760. So I get a volume of 4.94 liters. Which would be kind of a lot. Look at this. So this is just a small little amount. Now you might have had a chance to weigh that in a chemistry lab. That's not a lot of metal. And this is liters. If you think about your little small Erlenmeyer flask, you guys in chemistry lab are using 250 milliliters or even as much as 500 milliliters if you were, well, we've at least had them out there. This would fill those containers almost 10 times, or at least. So that's actually quite a bit of hydrogen coming out that's being made. All right, back to this. Next thing we're looking at is a few definition terms. Now we do have math problems that the book introduces with on these, but we're not really going to use them. So we're just going to introduce the concept. All right, so diffusion's the first thing that we're showing here. Now, what we're talking about when we talk about diffusion is the fact that, well, if we have two containers of pure gases connected to each other, we have a little valve in between them that's closed, there's no reason to suspect that they would mix. But as soon as they open, we would expect them to eventually get to the point where it's about 50-50 mixture of the two gases on both sides. Well, diffusion is actually just the technical term saying that the smaller molecule, smaller size or smaller molecular weight, will move faster at a given temperature. Therefore, that instant that valve's open, for a small fraction of time, there's going to be a lot more of the impurity on the one side than the other. Or what we're going to say is, we would get to eventually 50-50 on both sides, but at least for a moment, we're going to be higher on H2 on the one side than we are of O2 on the other. So it's not an equal distribution. The diffusion is saying that the smaller molecules, smaller molecular weight molecules, move faster at a given temperature. Therefore, they will diffuse into a container faster. Alright, now that gets related to another term that kind of does the same idea in the sense that the smaller molecular weight is faster, but it's effusion. Now, fusion is dealing with like leaks almost. So think of even a child's balloon for like a birthday party. If you think of one of the cheap ones, not that I shouldn't say cheap, the standard colored balloons, the rubberized balloons. If you had one of those at a birthday party and had some helium in it, by the next day it's drooping down on the ground. It's actually went from a relatively big balloon to its deflated one some. Yet if you had one of those metallic mylar balloons, they seem like they hold the helium longer. Well, they actually do. Turns out the rubber has little tiny holes in it. Little tiny holes. And the helium just leaks out of those holes. And the mylar has smaller holes, or less of them, so it holds it in there a heck of a lot longer. Now, something you can notice, and I always thought this was neat because I didn't realize it until I actually started doing chemistry. Let's say I had two balloons that were relatively the same size, so maybe more like this. And let's say one of them was pure helium and the other one was just air. Well, obviously the helium is floating in the early in the day, and the air is not. But what I want you to focus on is later on, like a day later, you will notice the helium balloon deflates faster. This is why it's kind of showing it smaller over here. And yet the one that's full of air might not deflate much at all, or it's going to deflate slower. Well, it is, the air is leaking through. The gases are going through little tiny holes, and the smaller the molecule, less molecular weight, the faster it goes through. Well, there is this nice little relationship. That's what they're shown down at the bottom. So the rate of effusion is related to the molecular weights of the two gases. It's the square roots of them. And you can use that to calculate molecular weights relatively accurately if you have the exact same container. Now, your book does a lot with it. I don't really do much with it because there's other ways of actually applying this that we're going to look at into later parts of chemistry, Chem 2 type stuff. So we're not going to do anything with the rate of effusion. Alright, but we are going to talk about some of the cool little features it leads to. Alright, so depleted uranium gets used for a lot of things in military, and purified uranium gets used in weapons. The ones that are bad for the environment and bad for everybody, the nuclear weapons. Alright, this is a technique that was used to develop to actually purify it. Turns out uranium-238 is relatively safe. It doesn't really get used in weapons other than they use it as a metal additive on like armor piercing round type things. It's something to do with the density. So they need to get a higher concentration of uranium-238, and the 235 will go to a nuclear reactor as fuel. Alright, but they need to separate them. So what they do, and this is something that was perfected back in the 40s even, so Manhattan Project era. We have a giant container, and we're going to actually get uranium hexafluoride in a molten form, maybe even gaseous, and it's going to be fed through here. Now, inside this little tube are little tiny little holes. Now, there's going to be some uranium-238 and some uranium-235 go through. But uranium-235 is going to go through faster because it flat out weighs less. So if we do enough of these over and over, we'll get mostly just depleted uranium-238 through the central one, and on the outside, lighter ones, the uranium-235. It does a really good job of separating the two. Alright, that was an application. Now we're going to talk about what the gas molecules actually do in a container at that microscopic scale, so we can understand when the ideal gas law breaks apart. So what I mean by this, we back up. I know the ideal gas law was just simply, I dragged my pen on the screen. The PV equals nRT equation? Well, if I rearrange that, we have that R equals P over V over NT. What I want to talk about is why at certain pressures and certain volumes and even certain temperatures, when they're at such extremes, why is that not always that 0.08206? Alright, so to understand what's going on here, we're going to talk about what the gases are doing. That's what my little 5 postulates here. So first one, gases are composed of molecules that are in continuous motion, traveling in straight lines and changing directions only when they collide with other molecules or with the walls of the container. So a given box with a gas, a given box with a gas in it. We're saying the gases are just moving nice little billiard ball type things. They don't change directions, they're perfectly straight line. They only change when they hit something like other gas molecules or the walls. Alright, number 2, the molecules composing the gas are negligibly small compared to the distance between them. Or what we're saying is the particles are so small we can actually just ignore their size in our calculations. Third one, the pressure exerted by a gas in a container results from the collisions between the gas molecules and the container walls. So pressure is just collisions. The more collisions, the more the wall stays out. 4. Gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, the collisions are perfectly elastic. So when I was showing them bouncing around up there in that little diagram, when they hit, they leave with all that energy. They don't transfer any energy into the walls, and they don't transfer any energy when they collide with each other. They just are perfectly elastic. They bounce right off. And then 5, the average kinetic energy of a gas molecule is proportional to its temperature. Alright, turns out all those little postulates there, when you put the gases in a situation where those rules break down, we're going to see that's when our gases stop behaving like a ideal gas. Alright, so we're going to talk about that and explain it with this concept of what our laws we're talking about. So our first little law we introduced dealt with increasing the temperature, and that caused an increase of pressure. Well, what we're saying here is, alright, we got our baseline here. We got a certain number of collisions going on. Alright, if we heat it up, molecules will move faster. If they're moving faster, they're going to hit the walls more often. And we just said on this previous one, the third one, pressure is just resulting from the collisions. So if we double the collisions, we're going to double the temperature. Or if we double the collisions, we're going to double the pressure. Alright, boil was one of the middle laws we studied. That was the pressure and volume. So if I have a certain pressure and a volume, if I cut that volume in half, now all of a sudden I'm going to double those collisions, because we're going to get to those walls that much quicker. So that should have doubled the pressure. And the last one, so we have our baseline. If I want to increase the size of the container and keep the exact same number of collisions, I need to add a lot more air, or double the amount. I've got to double the amount of gas molecules to keep the number of collisions to be exactly the same. Alright, that's explaining what we just had with the postulates. But now if we stop to think about what these little particles are, we can start to understand why it breaks down. The easiest one to see, really, is why when it breaks down is this volume. Now, volume, and what this says is, as that volume gets smaller and smaller, the pressure, the collisions get more and more and more. So as the volume gets smaller, so if I say this is my column, as my volume goes smaller, pressure goes up exponentially. Well, what we're ignoring in all this is eventually we're going to get to the point where the gas molecule's volume suddenly becomes significant compared to the size of the volume of the container. So we were able to neglect their size for a time, but eventually we're going to get to the point where the only thing left is the actual gas molecules. So we can't decrease this down to 0, because the gas molecules must occupy some space. So what happens when we get to the point where the volume starts to matter, the volume of the gas molecules themselves start to matter, suddenly that ideal gas law falls apart. Alright, so there's a few little situations like that tell us that the gas law is going to fall apart, and when it does, we have to solve it a little bit differently. So extreme pressures is a good way to see that the ideal gas law falls apart. Higher the pressure, the less likely you are to have your gas behaving like an ideal situation. Now these are really high pressures. You'll notice here, this is 200. You know, atmospheric conditions are here. We don't experience much beyond that. So these are very high pressures. But once we get super high, we get tremendous fall down on whether or not we're going to behave like an ideal gas. Well, years ago, there was this guy, van der Waals, who told us how to figure this all out. And he actually took our ideal gas law and he added these corrections to it. It's this term here and this term here. It's just correcting for the attraction of the molecules and for the volume of the molecules. Because the volume I just talked about, attraction, what we're talking about here is the molecules themselves are actually chemically attracted to each other, or physically attracted to each other. So there is an attraction, almost like a magnetic pole between molecules. It's just that it's a very small pole. But if we get slow enough molecules or low enough temperature, suddenly those attractions become noticeable and they start changing the ideal behavior. Alright, to see how this affects our chemicals, or our ideal gas law, we're going to actually do a sample calculation. Alright, so. Oh, I went too far. There it is. Alright, so I need a calculator. And let's make this a bit bigger. There we go. Alright, so at first, we're going to look at this and just calculate the pressure of the CO2 using the ideal gas law. So we're going to use PV equals nRT and solve for the pressure. Alright, so I have a volume of 4.25 liters. And I have an N of 3.46 moles. Our R is that 0.8206, and a temperature of 229 plus 273. So we're at an elevated temperature, and we're got a very small volume. So let's see what this pressure actually is. So I'm going to take that temperature, multiply it by the R, and that 3.46, and then divide this by 4.25, and we see that this pressure is 33.5 liters, or 33.5 atmospheres. Alright, doesn't seem like a lot, but if I back up to that slide that had that little bit of a curve to it, we see that that probably is gonna potentially be a bit of a difference. We're going to see what it actually is with this correction. So the corrected van der Waals pressure equation is what we call it. I'm going to write it right here. Pressure plus, it's AN squared over the V squared. And then it's V minus NB equals nRT. And then I have some A's and B's here. We're going to scroll down a little so we can do this. So we're going to still solve for this pressure. I have this first correction factor. A. My N is the 3.46 moles squared. And V is the 4.25 liters. Alright, that is the P plus AN. Alright, the V is 4.25 minus the N, 3.46, and this B, 0.0427. And that's going to be equal to the same nRT that we had up here. Alright, so I have 3.46. Actually, let me clear this so we get nothing on the screen. 3.46, the N, times the R, 0.08206, times the temperature, 502. Alright, this is everything over here. So now I'm going to divide by this term, divide by, in parentheses, 4.25 minus a second set of parentheses, 3.46 times 0.0427 parentheses equals this. And now I'm going to subtract this term, minus, in parentheses, 3.59 times 3.46 squared divided by 4.25. I didn't put that in parentheses, but that should be squared as well. Squared. I get a second pressure of 32.3 atmospheres. Very little change, but it is a change, and that would be a more accurate pressure under those extreme conditions. Interesting thing is, if I'm doing a multiple choice test, I am actually calculating this and then looking for a number near that, because we're not expecting it to change much unless this is a really big number, or we got a very high temperature or something like that. We need some extreme conditions to be a drastic difference. This really isn't that drastic. Alright, that is everything in our gas laws. We're ready to actually practice some problems.